In this example, I want to show you how to use a pre-trained convolutional neural network as a feature extractor for training an image category classifier. As I mentioned, a convolutional neural network is a powerful machine learning technique from the field of deep learning. CNNs are trained using large collections of diverse images. From these large collections, CNNs can learn rich feature representations for a wide range of images. These feature representations often outperform handcrafted features such as HOG, LBP, or SERF. In order to utilize this power of CNN without investing time and effort into training, it's possible to use a pre-trained CNN as a feature extractor. In this example, images from a flowers dataset are classified into categories using a multi-class linear SVM, which is trained with CNN feature extracted from the images. So instead of applying handcrafted features like LBP, HOG, or SERF, we use a pre-trained CNN, and this CNN can be used as a feature extractors. So we give it some images and we use the activation function of some layers as the extracted features, and then we give it to the SVM or multi-class linear SVM in order to classify it into the target classes. So this is the URL of the dataset. You can download it by your browser or you can download it by Matlab. You can see here by using web save, I use this URL. I give this URL to the web save function, and this is the full file address of the destination. And since it's a RAR file, after the download I want to unzip it and put it inside this download folder. Now load the dataset using image data store to help us manage the data. As you know, image data store operates on image file locations, and images are not loaded into memory until the read procedure, so it is very efficient for use with large image collections. Okay, now if I check image data store, you can see that we have 3,670 images inside this data store, and these are the labels. Let's check how many labels we have here. Let me first display one sample from this dataset. I find one image inside the image data store which has label equal to this one, and then I read that image and display it by imshow function. Let me find out how many images for each categories we have in this dataset by using count each label function. As you can see, we have 5 different type of flowers, and for each categories we have different number of samples. For example, 633 images from this category. We have 641 roses. We have 699 images from the sunflowers category. When you don't have equal number of images in each category, it is better to adjust it in order to balance the number of images in the training set. Also, I want to reduce the time that it takes to run this example. So first I determine the smallest amount of the images in a category, and I limit the number of images to reduce the time it takes to run this example to 100 images. And here, by using split each label, I only select 100 images from the each category and put it in the IMDS. So instead of using the whole data set, we only select 100 images per category. Let me run this part. As you can see, now inside the image data store we have equal number of samples per category. Now I want to load a pre-trained network. There are several pre-trained networks that have gained popularity. Most of these pre-trained networks are trained on the ImageNet dataset, which has 1000 object categories and 1 million training images. In this example, I want to use ResNet 50. So by using this line, I can load the pre-trained ResNet 50 into the workspace. There are some other popular networks trained on ImageNet dataset, such as AlexNet, GoogleNet, VGG16, and VGG19. Let me visualize some part of this network for you. As you can see, this is the input layer. Then we have the first convolutional layer, batch normalization, ReLU, and max pooling. Then the architecture divided into two branches. One of them is skip, or yes, there are some layers here and a lot of other layers in this branch, and then they again add to each others and again split it into other sections. You can see the other part of this architecture. As you can see, the ResNet 50 has many layers. And in the end of the architecture, we have a fully connected with 1000 neurons, a softmax layer, and a classification layer. The first layer defines the input dimensions. Each CNN has a different input size requirement. Let's check the first layer of ResNet 50. As you can see, the input size of this ResNet is an image with 224 pixels by 224 pixels, and the input image should be RGB. So in order to put an image inside this CNN architecture, you should resize it to these values. The final layer is the classification layer, and its properties depend on the classification task. So in this example, the CNN model that was loaded was trained to solve a 1000-way classification problem. Therefore, the classification layer has 1000 classes from the ImageNet dataset. Let me show you. As you can see, there are 1000 classes in the last layer. So pay attention that this CNN model is not going to be used for the original classification task. It is going to be repurposed to solve a different classification task on the flowers dataset. Let's prepare the training and test image sets. For this purpose, split the sets into training and validation set. We want to pick 30% of the images from each set for the training and the remaining 70% for validation. We randomize the split to avoid biasing the results. I use a split each label function and use 30% of the images for training and 70% for testing. As mentioned earlier, Net can only process RGB images that are 224 by 224 pixels. To avoid receiving all the images to this format, use an augmented image data store to resize and convert any gray images to RGB. The augmented image data store function can be used for additional data augmentation as well when used for network training. So here I called augmented image data store function and give it the train set and the size of the target size, and also I ask it to perform color processing, convert grayscale into the RGB. If there are some grayscale images in the dataset, they will be converted into the RGB format. I should do the same thing for the validation or test set. Let me run this part. Now we have augmented test set and augmented train set. In order to extract training features from the CNN, as you know, each layer of a CNN produces a response or activation to an input image. But there are only a few layers within a CNN that are suitable for image feature extraction. Of course, the layers at the beginning of the network capture basic image features such as edges or blobs. Let me show you how we can visualize the network filter weights for the first convolutional layer. This can help you to find out why the feature extraction from the CNN work so well for image recognition task. So we select the weights of the second layer, the first convolutional layer in fact, and as you can see, when we visualize them, there are some filters for finding the edges, for example vertical lines, horizontal lines, and some blobs. For example, if the image contains some green area in this part or red area in this part or some other type of the features. But as you can see, these are elementary features because we extract them from the first convolutional layer. So as you can see, The first layer of the network has learned filters for capturing blob and edge features. These primitive features are then processed by deeper network layers, which combine the early features to form higher level image features. These higher level features are better suited for recognition tasks because they combine all the primitive features into a richer image representation. So we never use the features of the first layer of the CNN because it is very simple and primitive. You can easily extract features from one of the deeper layer using the activation method. Selecting which of the layers to choose is a design choice, but typically starting with the layer right before the classification layer is a good place to start. So in net, the layer is named FC1000. Let's extract training features using this layer. As you can see, net point layers, we have 177 layers, and this is the name of the layers that I want to use as the feature extractor. So as you can see, I use activations method. This is the name of the network, and I gave it the augmented training set, and I select this layer. So the neuron activations of this layer can be used as the feature extractor, and the extracted features will be stored in training features. The mini batch size and 32 can be used in order to speed up if you have a GPU. And I want to store the extracted feature as a column vectors. So for each image we extract some features and it will be stored in separate columns of the training features. Let me show you. We have 30 images per each categories, and for each one we extract the activations features from the FC1000 layer and put it in the different columns. Okay, training features, where is it? Training features. As you can see, we have 5 categories, each one 30 images, so we have 150 different columns, and the size of each column is 1000 feature. So this is the feature size, and this is the number of samples in the training set. Now let me train a multi-class SVM classifier by using these CNN features. So here we get training labels from the training set. We need both of the truth label and the features in order to train a SVM. By using this method, we train a multi-class SVM. By this configuration, we use fast linear solver and set observation in 2 columns to match the arrangement used for training features. Here, as I mentioned, the features are stored in columns, so here we mentioned that the observations are ordered as in columns. Let me run these 2 lines. Now the classifier is trained, we can use it to classify some samples. So here I repeat exactly the same procedure for the augmented test set. So extract the features and save them in the test features, and then I will give this test feature to the classifier that I trained here and compute the prediction labels. These prediction labels can be checked with the real or truth label of the test set, and we can display a confusion matrix in order to find out for each category how percentage is classified correctly. Let me run it. So this is the confusion matrix. So for example, 82% of the images are belong to the category 1 and are correctly classified as category 1, but some of the other ones are classified as category 2, 3, 4 or 5. So the worst case is here. Only 75% of the images are correctly classified for category 3. If we want to find the mean accuracy, we can write mean diagonal part of this confusion matrix. %82 is the accuracy of the model. Let me apply the train classifier on one test image. Here I read the first image of the train test set, and also I display the truth label of this sample. Now I extract the features. First I resize it by using augmented image data store, and then I extract the features related to this image, and now I can give it to the classifier and check the predicted label. As you can see, the predicted label and the truth label are the same in this example, but the mean accuracy of the system is only 82%. So in this example you learn how to use a pre-trained CNN model as a feature descriptor or feature extractor. We extract some features by activation function, and then we give these extracted features to a CNN or multi-class CNN in fact, and perform the classification and show you the confusion matrix.